Assalamu alaikum, dear friends and students. Today we will discuss the part B of the reactions of aldehydes and ketones. In the part A, we have discussed the reaction of aldehyde or ketone with the water molecule and with the alcohol, with the cyanide, with the organometallic compounds, and we also discussed the reduction of aldehydes and ketones. So what was the common in all those reactions? It was the attack of the nucleophile and the formation of the tetrahedral product. That was a simple addition reaction. And now we will explore some more chemistry on the reactions of aldehydes and ketones. In this lecture, we will discuss the attack of the primary amine to have the imine formation, to have the attack of the secondary amine, to have the inamine formation, and then we will also discuss the attack of the hydroxyl amine, hydrazine, and then we will discuss the Wolff-Kishner reduction, Wittig reduction, and oxidation of aldehyde and the Baeyer-Villiger oxidation. So now let us start our lecture with the addition of the primary amine. Aldehydes or ketones are reacted with the primary amines to give imines. So this is the general reaction. This is the aldehyde or ketone when reacted with primary amine. In a simple condensation reaction, we have this imine. This C double bond N is called imine, and the byproduct is the water. You could simply see these pink two hydrogens and this oxygen. They made the water molecule, and this red colored nitrogen has been replaced with this oxygen. So this is the overall. This is a condensation reaction. And this C double bond O, which is called the carbonyl, has been converted into the C double bond N, which is called the imine. What should be the mechanism? As we have already discussed, that when we have the acidic medium in the reactions of the aldehydes and ketone, the first step must be the protonation. So the lone pair of oxygen of the aldehyde or ketone will attack the proton source to have this protonated carbonyl species. Now this has become much more electrophilic, which will be immediately captured by the amine, the primary amine, to have this tetrahedral intermediate, because this amines nitrogen's lone pair will attack this carbonyl carbon. This pi bond will be broken to have this OH group here. And now in the next step, this there will be the proton shifting. This H will shift to this hydroxy to have this oxonium ion, and then the lone pair on this amine will collapse here to leave the water molecule off. So this is called the iminium ion, because we have already discussed what imine is. C double bond N is called imine, and we have this positive charge on nitrogen. So this is called iminium ion. So water which has just been released will serve as a base to deprotonate this iminium ion. It will pull the proton from here, so leaving the neutral imine as the main product. Now let us discuss the attack of the secondary amine on the aldehyde or ketone. It will give the inamines. So this is a general reaction. This is the aldehyde or ketone, and this is the general structure. For the secondary amine, you could see there we have only one hydrogen, not the two hydrogen, and we have this inamine bond. What is inamine? As the name suggests, we have the double bond in and amine on the same carbon. So this is called inamine. So now let us discuss the mechanism. Again, it is very much common with the primary, like we had the mechanism for the primary amine. The first step will be the protonation. The second step will be the nucleophilic attack of the amine. The third step will be the proton shifting. This H will shift to this OH. The fourth step is again the similar. That is, the lone pair of nitrogen will push the water molecule off, and we have this intermediate. Now, there lies a difference, because if you consider with the primary amines reaction, we had hydrogen here, because in primary amine we have two hydrogen and one alkyl attached to the nitrogen. So still we used to have one hydrogen, which was abstracted by the water molecule to have this C double bond N as a neutral compound, which was called imine. But in secondary amine, we do not have the hydrogen that is possible to be removed here. So what the water that has been just removed will pull the proton from where it will pull the proton off. So it will take the proton from this alpha position with respect to amine. So this hydrogen being acidic in nature, and the only option available, the water will remove this hydrogen, and we will have a double bond between this carbon and carbon, and a single bond between C and N, which is called in amine. In because of alkene, amine because of amine. So there is the only difference in this last step for the secondary amine with respect to the primary amine. Well, amines or enamines may be hydrolyzed by adding excess water in the presence of catalytic amount of acid. So the way we made the amine or enamine may be reverted back if we add the excess water under acidic conditions. So amine will give us back the aldehyde or ketone and the primary amine, and the enamine will give us back the aldehyde or ketone and the secondary amine. Now let us discuss the addition of the hydroxylamine. If hydroxylamine is added to the aldehyde or ketone, the product is called oxime. This is a general reaction. We have this aldehyde or ketone and hydroxylamine. Again, it's a condensation reaction, and this H2 and O will be knocked off as a water molecule to have the C double bond N and OH bond, which is called oxime. And the mechanism of this reaction is similar to the mechanism with the primary amine. The only difference is that in the primary amine we had NH2R, here we have NH2OH. So this OH is, if we replace this hydroxy with the carbon chain, and the mechanism will remain the same. For the addition of hydrazine, we have the hydrazone formation. So this is a general reaction in which you could see the NH2. This molecule is called the hydrazine. When this condenses with this aldehyde or ketone, we have the C double bond N and NH2 with the departure of water as a byproduct. This species is called hydrazone. And focus the spelling of the hydrazine and the hydrazone. There is a slight difference, only the difference of I and O. Again, the mechanism is same as for the primary amine or as with the hydroxylamine. The difference is that in the primary amine we had the R group here in place of this NH2, and in hydroxylamine we had the OH group here. And now in hydrazine case we have this NH2 group here. The nucleophilic side, that is this NH2, is same for all the three reactions. So before proceeding further reactions, let's recall some basic terminologies. If we have the aldehyde condensed with the primary amine, the resulting amine is called aldimine. Here ald has come from the aldehyde because we have this methyl and hydrogen here, and amine has come from this condensation with this primary amine. And if we treat it with the hydroxyl amine with the aldehyde, the resulting oxime will be called as aldoxime. And if we treat the hydrazine with the aldehyde, the resulting hydrazone will be called aldehydrazone. And now if we replace the aldehyde with the ketone, so the prefix will change, and this time we will call the ketamine for the ketone and the amines condensation, and the ketoxime for the ketone and hydroxyl amines condensation to have the oxime with the ketone functionality, and the kethydrazone for the condensation of ketone and hydrazine. So remember these 6 names which give and the structures description within their own names. Now let us discuss the Wolff-Kishner reduction, uh, in which we have the deoxygenation of the aldehyde or ketone. With the deoxygenation, it means the removal of this carbon and oxygen, and we have the entry of 2 hydrogens. So this is also called the reduction, but it's better not to use the term reduction, because in reduction we have one level down, that is the ketone is reduced to the alcohol, but here 2 levels are down, so it's better to call the deoxygenation, although the name has the word reduction. So it is treated with the hydrazine in the first step, and you know the what should be the product. If you treat the aldehyde or ketone with the hydrazine, it must be the hydrazone, But in the second step, when you treat with the hydroxide, there will be a formation of this alkane if the two R and R prime are alkyl, and nitrogen gas departure. So this reaction has a good level of entropy because of the release of the nitrogen gas. So what is the mechanism? In the first step, the aldehyde ketone is treated with the hydrazine to have the hydrazone, whose mechanism has already been discussed in the prior slides. And now in the second step, the hydroxide, it attacks the terminal nitrogen's hydrogen. So as a result, this NH bond will break and there will be a new bond between NN, which is a pi bond, and then this C and pi bond will break and we have the protonation on this carbon with the help of the water molecule to afford this intermediate. And now the second mole of hydroxide will again come to attack the terminal hydrogen, and this time we will be having the triple bond between the nitrogen, and this CN bond will be broken. So we have this carbonyl intermediate, but remember, uh, although this is very unstable intermediate, but this will form because of the release of the nitrogen gas. So this is the driving force for this step. Nitrogen gas release is a is gives the possibility to have this carbanion generated for a little time, which will be immediately protonated with the help of the available water to have the final desired product, in which we overall have the two hydrogens in replacement of the doubly bonded oxygen. So overall we have the deoxygenation reaction, and the whole process is called Wolff-Kishner reduction. Now let us discuss the Wittig reaction. This reaction is also called the Wittig olefination because we have the formation of the olefin, that is the alkene, from the carbonyl. If you consider the general Wittig reaction, just consider the red molecule at the time, which is the aldehyde ketone, and this pink molecule, which is the alkene. So we started from here, we ended to alkene, and the left hand side portion of alkene has come from the corresponding aldehyde ketone. The right hand side portion of the olefin or the alkene has come from the unit, and this is called the unit, the blue species. We will discuss what unit is in the next slide, and the byproduct for this reaction is triphenyl phosphine oxide. So now let us discuss what unit is and the phosphorus unit. Basically, unit is a electrically neutral species which has a positive and negative charges on the adjacent atoms, and if the positive charge center is phosphorus, it is called phosphorus gelid. So if you consider this species which is phosphorus gelid, it's because if you draw its resonating forms, you could see the pi bond is broken. We have the electron density at this carbon, so this phosphorus will be positively charged and carbon will be negatively charged. So this is called the phosphorus gelid. And how is it formed? Basically, first of all, it's a simple SN2 reaction. This triphenyl phosphine, when attached to this alkyl halide, this halogen is displaced and we have this PPH3 group here, the phosphorus and the three phenyl groups. We have the positive charge on the phosphorus because the lone pair of phosphorus has been added, has been involved in the bonding with the carbon. And then this hydrogen, now it has become quite acidic because in doing so we will have the double bond between the carbon and phosphorus. So when we treat with the base, this hydrogen will be abstracted. We will have the negative charge here on this carbon, and the adjacent atom, that is phosphorus, has the positive charge. So overall it's called yelid. And as we have discussed, this phosphorus yelid may also be written like this. So these are more examples. When this triphenyl phosphine is treated with methyl bromide, we have this compound, and then if we treat with the phenyl lithium serving as a base, this hydrogen will be removed to have this phosphorus yelid. And remember one more thing, whatever group is attached to this phosphorus, for example here R double prime, C negative and R triple prime, it's basically general. If you consider here, we have CH2 negative, so this group will be replaced with the carbonyl oxygen to have the corresponding alkene. Now let us discuss the mechanism. Once we have formed the yelate, and we know that this yelate is nucleophilic from this carbon and electrophilic from this oxygen. So it's a concerted reaction in which this nucleophilic carbon of the yelate will attack this carbonyl carbon, and in return we have the nucleophilic attack from this pi bond to this phosphorus to have a four-membered oxygen and phosphorus containing ring, which is called the oxaphosphetane ring, and it is very much strained, very much unstable, so it will be immediately opened uh, in this manner that we have the carbon-carbon double bond and phosphorus oxygen double bond to have this alkene and this triphenyl phosphine oxide. And remember, we will get a diastereomer, a different more diastereomers of the alkenes because it depends upon the formation of the carbon-carbon double bond about the orientation of this R and R prime. It could be E isomer or it could be Z isomer as well. The driving force for this particular step is the formation of phosphorus oxygen double bond, which is the strongest double bond in the organic chemistry. Now let's discuss how to plan a Wittig synthesis. Suppose we want to make this olefin, this alkene, using a Wittig reaction. So if you cut this carbon-carbon double bond from the middle, you will have two fragments, one fragment on the left hand side, one fragment on the right hand side. So if you consider this left hand side fragment to be the positive center, that is the electrophilic center, it will be a carbonyl, that is cyclohexanone, and this carbon will be negative fragment, that is the negative synthon, that is the negative yelate in this case. And now this yelate will be made from the corresponding haloalkane and the triphenyl phosphine. So this is the route 1. In the route 2, the reverse is the case. Rather than considering this carbon to be the electrophilic and this carbon to be the nucleophilic, we reverse it. Let's consider this carbon to be nucleophilic, that is yelate, which may be made from the corresponding bromocyclohexane, and this carbon to be electrophilic, that is the carbonyl in this case. So now discuss both routes. In the route 1, when we have this butyl bromide treated with triphenyl phosphine, we have this intermediate which will be converted into yelate using butyl lithium. This hydrogen will be removed to have C negative and P positive linkage, and then this nucleophilic carbon will attack this carbonyl carbon. As a result, this oxygen will attack this positive phosphorus to have four-membered ring, which will collapse to have this final product, which is our desired product. In the route 2, this triphenyl phosphine will attack to this secondary carbon to have this substituted product, and this butyl lithium will extract this proton from here to have this phosphorus yelate, and now this phosphorus yelate will attack this aldehyde, this butanol, to have our desired product. So there are two routes to make this particular molecule. Now let's discuss the oxidation of aldehydes. Remember, this reaction is specific to the aldehyde, in which we treat aldehyde with the potassium permanganate under alkaline condition to have this carboxylate salt, and which upon workup gives us the carboxylic acid. We may also use the silver oxide in replacement of the potassium permanganate. Remember, this reaction is specific to aldehyde. If we treat the ketone with the potassium permanganate under the alkaline condition, we will not get the carboxylic acid. Either the reaction will not proceed, or the carbon-carbon bond of the ketone may break to have different small molecules. So in both cases, we will not get what our desire is, that is to acquire the carboxylic acid. Now let us discuss the Baeyer-Villiger oxidation. This reaction is specific to ketone to have the formation of the ester using this peroxide. So in overall, you could see there is an entry of oxygen between this carbon and carbon bond to have this ester. But how this transformation has achieved? So let us discuss its mechanism. The first step is the reaction of the ketone with the peroxide. It is in the protonation step, in which the carbonyls oxygen is protonated from this peroxide to have this protonated carbonyl and this anion. And now this anion will attack this protonated carbonyl immediately to have this intermediate. Here we have the migration of this R prime group, this alkyl group, to the adjacent oxygen. As a result, this oxygen-oxygen bond will be broken to have this carboxylic acid as a byproduct and this ester as the final product. You could see this R prime, it came from the adjacent carbon. It came from this carbon to this oxygen. So this R prime came from this carbon to this oxygen, and when this R prime moved from this position to the adjacent position, the pi bond has been formed here because of the collapsing of this hydrogen and oxygen bond. One thing you could be thinking at this level, why R prime is moved and why not this R group moved? Well, this is the question of the migrating group ability. The group which is good at migration will migrate, and the migrating group ability is tertiary alkyl group migrates preferably over the secondary alkyl group, which in returns migrate preferably over the phenyl group, and then phenyl group preferably migrate over the primary group. So this is the reason, if you see this main reaction, this is the reason that we showed the migration of phenyl and not migration of the methyl. So there is oxygen between this phenyl and carbonyl. If the methyl group migrated, we had the oxygen between the carbonyl and the methyl. So remember to show the oxygen between carbonyl and that alkyl group that has been migrated. So in summary, we have discussed the reaction of aldehyde or ketone with the primary amine under acidic condition to afford the amine, and with the secondary amine we have the enamine. With the hydroxylamine we have the oxime. With the hydrazine we have the hydrazone, and with the hydrazine and the potassium hydroxide we have the deoxygenation. The reaction is called the Wolff-Kishner reduction. With the potassium permanganate, if this R is H, that is for the aldehyde, we have the carboxylic acid, and when treated with this peracid, we have the Baeyer-Villiger oxidation to have this ester. So this is all for the part B of the reactions of the aldehydes and ketones. In next part, we will discuss the aldol chemistry and the manic chemistry. Thank you.